Thank you very much for the kind introduction, for being here, for the interesting workshop so far. Am I audible at home?
So can you hear? Yes.
Okay, cool. All right. So I think it's a piece of popular wisdom that many people would want to accept. 1A, humans understand language. But I think that people are at least a bit iffy, if not rejective, about 1B, language models understand language. Although people frequently say these kinds of things, like we heard it in the talks before, I do it all the time, but maybe if you're really pressed, do language models actually understand language? Maybe people think, not so sure, maybe not. But the real question is, why is that so? And some people feel that there is this something is missing intuition. And some people point out that this could be maybe a lack of grounding, like Emily Bender and Alex Koller in their famous octopus paper. More on this in a moment. And other people might think that maybe what is missing there is some kind of situatedness, where this could mean either being situated in a static or dynamic environment, or situated in an environment even with other agents, communicating agents, as expressed recently by David Schlangen and a couple of short papers. So if you're, who's familiar with the octopus argument? Okay, I thought that was maybe more of a thing. So 2020, Emily Bender and Alex Koller basically made the following, suggested the following thought experiments posed as two people stranded on separate islands, and they can communicate by some kind of telephone line that runs on the water, but a super clever octopus is listening in for a long time until it figures out basically to predict whatever A would say to B when they communicate. But then one fine day, A is in trouble, a bear shows up on this tiny little island over here and is threatening to eat A. So A says to B, I have a couple of sticks. How can I defend myself against the bear? And the idea behind this octopus argument is that the octopus at this point where it's actually listening in and giving the responses, so that A hasn't actually realized this until now, because it's out of distribution, has no idea what to say, because he's never seen this. And the reason why, so the authors argue, is because it lacks grounding. It has never seen the world. It has only listened into these communications. I feel like this is a maybe intuitive argument, but it really cuts no ice, because just a few years later, actual language models that have not been trained on any grounded input were able to tell you how you can defend yourself against the bear with some sticks, etc. And so I think what we really need is a more like an in-principle argument of what language models trained from pure text could acquire that could maybe make them eligible to something like understanding language. So I want to put up my philosopher's hat today. I mean, that's pretty unexpected, maybe on a social robotics conference, but I think it's going to be fun, I hope, to reflect on the senses in which, so this is like this index S, the senses of understanding that there are. We're really actually going to look at some philosophical literature on this, and to ask whether there is a reading of understanding so that the first and the second sentence could at the same time be true. But we also want to make room for the fact that even if you may apply the same sense of understanding, it might turn out to be a different kind of understanding after all when you apply it to humans or to machines. Right? So we also want to ask, when applied to humans and LLMs, are these specific readings of understanding eventually the same? And I'm going to argue probably not. And this will have basically world models and representation learning come in. So there is an ML kind of flavor to it. Okay, so let's do a bit of analytical philosophy first and look at the kinds of senses of understanding that philosophers of science have recently started to distinguish. So first of all, there is a prominent sense of understanding something, of being able to give an explanation. And yeah, language models can often give you explanations of even why they said something, or why some people might use language in a particular way. There is, you could say that explanatory understanding is a special case of use understanding, which is the sense of saying that you can use X itself or information about X to achieve some goals. And these could be verbal. So you have the capability to answer questions about it. So similar to explanatory, but maybe more open-ended. Or maybe guide your behavior. Well, LMs, unless you give them tools, which I brushed to the side for the moment, right? Can't really interact with the world. So it's really comes down to this. And recently, David Chalmers, famous analytic philosopher, has answered the question for himself: do LLMs understand? Well, to a certain extent, they have this explanatory and this use understanding. So maybe if we say like LLMs understand when we mean like in general reasoning context, this is what we have in mind. But if you fetch a person from the street and you talk about understanding, they probably don't mean explanatory understanding or use understanding, because it seems like the most prevalent intuitive understanding of what it means to understand something is to have this subjective feeling of this makes sense to me, right? And for that really reason, because it seems like almost phenomenological philosophers of science have long eschewed talking about understanding and rather wanted to talk about logical explanation and the like, right? Because it's like subjective, you can't really formalize it, right? But I do think that, or I mean, many people think that what's at the heart of our understanding of understanding is this feeling of everything making sense. More recently, in the literature, there's a predominant reading of what it means to understand in terms of what philosophers call a dependency model. And I'm going to latch onto this because I think that this is the closest or the best that we can work with in the context of machine learning, robotics, learning representations, etc. And I do think it also, at least partially, accounts for this intuition that understanding has this phenomenal component of everything makes sense in the following sense. So a dependency model is essentially a model of the counterfactual dependencies of whatever it is that you try to understand. So there's some phenomenon X, and you understand it when you know the factors that lead to it or would have led to it if things had been different, right? And in some sense, this relates to a sense of not being puzzled, because if you have such a dependency model and you see X happening in the world, right, you are not surprised. You have seen the factors that influence it, right? You minimize your surprise in an active inference sense if you have a reasonably adequate dependency model. And so I would really like to work with this. But then there's a challenge. Here, this is Elisa Yudkowsky, and I quote the plug from Les Wrong's blog post here, where he ascribes to Ilya Sutskever, no other than that, the idea that to learn to predict text in a language model is to learn to predict the causal shadow of which the text, the causal process of which the text is a shadow. So in other words, if you really master, let's say, the next word or next token prediction task, you will apparently almost indefinitely have to evolve the correct dependency model for language. So the intuition goes. And I want to challenge that. I don't think that's necessarily true. Or actually, I would like to argue that this is exactly not true if you only train on text. Okay, in order to do all of this, I would like to give you two arguments. It's quite a mouthful. One is an intuitive argument that you could use in a bar, maybe with non-experts, to argue for why, you know, in an intuitive sense, language models being trained only on text probably don't evolve some kind of phenomenological understanding. Maybe that's useful to you at some point in your life. You never know. And the second argument I'd like to give to you is like a minimum models argument. And I think that's much more useful when you actually talk to people from ML, maybe computer science, who care about world models that you can maybe learn through training a system. And it's much more technical. So let's start with the Japanese room argument. Who is familiar with the Chinese room argument? You probably have heard that in some kind of class, so not. Just a very brief reminder. This is targeted at the question of whether systems, usually computational linguistic systems, that use a rule manipulation, like a rewrite rule manipulation strategy, develop some kind of understanding. So the idea is that you have some experiencer in a Chinese room who does not know Chinese. So the story goes, people supply Chinese text. This person has been given, as part of the modeling setup, a set of rewrite rules, looks at the input, applies the rules, gives you some output. And since the rules are so good, the people feeding, you know, the input and looking at the output may think that there must be a person who understands Chinese. Why else could you give so high level input-output relations? But the experiencer itself, while applying the rules intuitively, does not develop any sense of phenomenological understanding of the language, right? So could we use the Chinese room argument immediately to talk about language models? Yes, we can. Yes, we can, but we shouldn't. So in this table here, you see a distinction between symbol manipulation, so good old-fashioned AI kind of rule rewrite systems. And on the other hand, you see like your deep learning, let's say more generally statistical learning approaches, right? And here's your Chinese room argument. And here down there, I mean, you don't see it, it's the Japanese room argument, which I'm trying to give you. So let me talk you how we want to go from here to here and why. So the thing about the Chinese room argument is that the rewrite rules were given ex ante, from the outside, exogenously. Like whoever did this, planned this Chinese room, right? They gave you the rules. You didn't come up with them. So for the experiencer, they can do their thing without ever having reflected on those rules. In other words, you have a narrow experience rule. But we can imagine a slightly different setting in which the rules are actually produced by the system, by the person who's doing that, right? And that might change things. You could also imagine other variation of the Chinese room where what you're giving is a more general rule from which the others would follow if you reason about it, right? And that changes intuition quite a bit. And I think if we want to evaluate like statistical learning models more fairly, we don't want to think of them as this narrow experience. If I give an agent the weights, then actually the forward pass or the decoding step in a language model is trivial. And you can imagine, yeah, this is something, you know, you can just do like this person in the Chinese room without knowing what you're computing. Like you're basically just computing a bunch of numbers and eventually maybe sampling from a distribution. Hooray. Language understanding? No. But I do think that when we think about language models, we think about them as a much more abstract concept that also encompasses the learning step. So imagine that we have an experiencer who not only experienced, given some weights, how it feels like to compute a forward pass, but how it would feel like to actually learn in the same way that the language model was learning, right? And to find the optimized weights themselves, basically, maybe implicitly in their head, and then to execute maybe a forward pass. And that's what I would like to call the Japanese room. And it would be basically trying to address the following question. Would a human experiencer necessarily, and I think that's important because extraordinary claims require extraordinary evidence, right? If such a machine would actually acquire phenomenological understanding, that would be quite an extraordinary claim. So would they necessarily develop understanding, in some sense, of language if they undergo the same learning and generation protocols as LMs with training data of perfect quality and unlimited quantity? So it's a limit experiment, like a limit thought experiment. And I'd like to focus on the question of whether they develop phenomenological understanding. Here's the first version of the Japanese room argument, which I think is slightly flawed. So imagine you don't know any Japanese. You're strapped in a room in front of a video screen. Japanese text is presented to you stroke by stroke. That's not necessary, but I think it helps get the intuition because the individual strokes in which you usually write Japanese characters, Chinese too, Japanese characters, are not necessarily meaningless as such, right? So this reflects the idea that the tokens that we usually use in LMs are also not meaningful per se. After each stroke that you see on the screen, like you do this, if you have to write Nihon, right? You start here and you see each next stroke appear on the screen. You're asked to actively predict the next stroke. That's the first version. And then you get feedback on whether this was correct. And then over time, you get better at predicting the next stroke. You can imagine like this. A little Fermi calculation here. So if we imagine that we would train an actual human on this task, it's roughly the same size as Llama 1 was trained on, then this would last around 400,000 years, which would bring us into the time of the early Neanderthals. So this is massive, right? It would not go through the ethics board. It's not an experiment that we're going to do, right? But this is roughly what you could imagine. So 400,000 years, poor Hank, the Neanderthal, is sitting there and is looking at the screens and is getting better and better intuitions. Okay, this is roughly the idea. This version of the Japanese room is slightly flawed, I believe, because it's more of the kind of RNN or LSTM style, right? Where every token is presented in sequence and you build an internal representation of what you have seen so far. I think, and this one actually asks you to actively predict the stroke, and I think that might make a difference in the intuition that we need to appreciate whether LMs could develop something like an internal understanding in a human sense. So let's imagine that the human experiencer is actually seeing a slightly different experiment that works like this, and is more geared towards transformers. So that you see on the text, on the screen, the text presented as a large grid of strokes, like in each individual token, so to speak, right? But presented in one shot. And you glance at it, maybe for 10 seconds. and then it disappears, and then another token shows up on the screen. And we measure your pupil dilation, your galvanic screen response, or actually maybe something like your EEG response on N400 amplitude, because we know it correlates with surprisal, right? And we give you an electric shock proportional to how surprised you were for 400,000 years until you're less and less surprised because you want to avoid these electric shocks, okay? If you manage to do that, reduce your surprisal at seeing the next token, would you think that you have understood language or understand what you see there? Me, not me, right? So it's a pretty hardcore experiment, I would think, right? Or thought experiment. But I think this is a very close analogon to how you could think of learning like a language model. But still, you could backfire and say, I cannot imagine that you can learn this task actually without any active prediction and cognitive control, and then it would lead to awareness and maybe some kind of phenomenological understanding after all. So then I would say, well, maybe you have to go some more extreme cases from cognitive neuroscience and look at how particular patients can learn stuff without any form of conscious awareness. This is a case of Eugene Pauly, for instance, who unfortunately had viral encephalitis, leading to severe amnesia, both retrograde and anterograde, lost about 10, 15 years of his memories, and was not able to form new declarative memories. But he was able to learn. So for instance, they moved house and he knew where the bathroom was because he could go there. But if you asked him where was the bathroom, he couldn't tell. And psychologists who accompanied him through later stages in his life also subjected him to discrimination learning tasks, which like this, there's two pictures always paired. Let's say picture of a dog, picture of a cat. And the researchers know dog is correct, cat is wrong. For someone, it's totally arbitrary. And they show these participants, right? And over time, you learn, okay, the dog is correct, the cat is wrong for a couple of, of these pictures. And normally, let's say for the size of what EP was learning, now they say neurotypical subjects can learn this in a few sessions and get almost everything correct. EP took 18 days to learn this at accuracy at 85%, but you had to explain the task to him all of the time. He had no idea that he's ever done this before. And when he actually reached 85% of accuracy, he was really surprised. How am I doing this? So just as a reminder of what we could potentially learn if our brain was not continuously mirroring us, maybe laying the credence to the fact that 500,000 years of being exposed to electric shocks to minimize the surprisal might give you learning without any subjective feeling of understanding what's going on. But it's a hardcore thought experiment. I agree. Okay. All right. So, but then the opposition could go, even if learning is sub-aware, Michael, in the limit, the actor must evolve mental representations similar to our human concepts, because otherwise they cannot solve the missing token anticipation. So this is, again, this idea of, if you want to do this right, it has to kind of reflect the original causal processes. So let me have a brief look at the minimal models argument. So the conclusion of the minimal models argument, I'm starting with this, is roughly this. And I think actually a version of this, many people would, in the ML crowd, I think would find rather intuitive, but I really want to give substance to it. And the idea is that even though humans and LLMs may be said to understand language in the same sense, namely in this dependency model sense, we're looking now at the world models that humans may evolve and language models may evolve. They have different language understanding unless the language model would have miraculously some internal inductive biases towards human-like concepts that are useful for tasks the system is not exposed to, which I think is very unlikely. So let's go through this maybe quickly, but just to show that this is actually a formally worked out analytical philosophical argument, or at least it's trying to be as good as it can. This is how it goes. So we'll assume that understanding means having a dependency model. Okay, and for ease of thinking about it, let's think about this as a structural causal model. Actually, dependency models are more general, but let's think about this as a structural causal model. Then what is a dependency model of language? That would be a structural causal model of the kinds of things that actually generate language out there in the world, whatever that is, right? So basically making us feel like we understand where that is coming from, these noises that I produce, etc., and how you have to respond to this. So another assumption that I think is easy to buy in is that dependency models, any kind of internal representation in humans and LMs must be kind of near optimum. It doesn't have to be perfectly optimal, but it's going to be definitely optimized in one case by evolution and ontogenesis, in the other case by training for whatever task they're doing. But here's an assumption that you might feel maybe less obvious in the first place, but I do think it is correct, that the human dependency model for language is very likely to share conceptual resources with dependency models for other tasks. We're not just language using agents. It would almost be folly if our internal wetware was using a particular kind of knowledge, right, just for language and not also repurposing for anything else and the other way around. So that would, however, mean, I think, as S5, that humans have dependency models that are probably structured hierarchically with certain latent variables that can reach out and explain different types of observations at different times. I'll give you a concrete example about this in a moment. If this is the case, okay, no, sorry, one more assumption. If you have different dependency models, then it's probably in the sense of, being near optimal, fair to say that dependency models with fewer variables and maybe lesser hierarchical structure or shorter path lengths in general are more economic, all else equal. So maybe at the same, modeling the same outputs or giving the same predictions, if you can do that with fewer variables and shorter path lengths, that's good. So I would assume that in general, these kinds of internal representations would try to minimize the number of variables that or representation, internal states that they're trying to compute and also the relations between them. But that would mean that the human dependency model for language is actually less economic than it is required to be if we are just looking at language understanding. And if you buy into that so far, which is probably too fast for you to really check, but then I got you, because then you would probably need to concede that the LMs from LMs dependency models differ from those of humans because they're either more economic than a human DML because the human DML is doing more than just predicting language, or that's pretty unlikely, they have been prevented from learning more economic dependency models, the LMs, by some inductive biases, either in the model architecture or maybe from the training data set, that has some kind of prevented them from optimizing their internal representations. Okay, this is my best attempt at giving an almost like very general in-principle argument why I would think that the understanding that language models might achieve by their training is almost certainly different from the understanding that humans achieve. But let's make this much more concrete. If I think about language and language use and the dependency model that probably human speakers have, I think of something like this. So this is actually what I earn my bread and butter with, that is probabilistic models of pragmatic reasoning. So essentially a pragmatic interpreter who is trying to figure out what a speaker meant by reasoning counterfactually about the other things that they could have said to eventually estimate likely causes, mental state descriptions, intentions, whatever you want to call them, causes of the observed speech behavior. Okay. And if we think about it in this way, then probably at least a part of the human dependency model for language has this structure. The speaker model generates an utterance. And this is causal. Now, I mean this really structurally causal model, not based on it. It's the speaker meaning or whatever mental state that is actually the cause of the utterance. Whether that's actually correct, like neurophysiologically speaking, doesn't matter. I think it's part of the way in which we do want to interpret language. And now we could ask, should a transformer architecture evolve a similar causal representation of that? So this is your causal architecture. Sorry, it's a transformer compute architecture feed forward. These are the words feeding in, right? Here you have your states in this purplish kind of thing. Then you would compute your attention and your MLP in these different layers, right? And eventually you maybe make a predictions about the next word. So we don't know yet, as far as I can say, how exactly to determine what each representation at each hidden state in each layer and each attention head actually means, right? Maybe we're getting closer with certain very interesting tools like circuit analysis, path patching, etc. But just imagine that we could, in some sense, say like, okay, here is the representation of this and that. Then one way of doing this and solving this problem of understanding speaker meaning from an utterance and using this knowledge to generate a next word prediction could be something like that. You have your original utterance in the input, sure enough. Then you could say like, okay, I want to reason about what the speaker could have said. So I generate a bunch of candidate meanings that the speaker could have. This is like trying to solve this Bayesian inverse reasoning inside the transformer architecture. You would then maybe generate alternative utterance counterfactually, compare them to the utterance that was said in order to infer by something like Bayes' rule, the speaker meaning, and then eventually make up your mind of what to say next, something like that, if this is a dialogical situation, right? However, actually computing Bayes' rule in this way, like reasoning backwards about what would have explained this utterance and therefore basing your choice on that, seems much less economic than just having Bayesian inference amortized. I mean, if this is just trained to figure out what the speaker meaning is and then make a decision on that. In other words, if it never actually uses any alternative any representation of speaker meaning or anything of these for any other explanatory purposes, it would be very unlikely if the system would evolve this type of representation than that. This is the hand-wavy argument that's trying to fill in what this more general argument, which I would actually like to defend, not this one, could try to capture. All right, so the take-home message from this would be, since world models for humans and LMs are optimized for different things, it's highly unlikely that the represented dependencies are the same. This is so naive that probably many people would have, like this formulation, so naive that probably many people would have accepted it in the first place. But I think that this argument that I presented here is trying to make this, give this some more weight and some more formal substance. Okay, conclusions. Do humans understand language? Yes. Do language models understand language? That depends. Probably not if you think like a phenomenological understanding, if you believe the Japanese room argument. Probably yes, but trivially so if you mean like having some kind of dependency model for the language. But then the next question is more interesting. Is the dependency model like a human? And my argument would have been likely not via the middle models argument. In general, let's be reminded that understanding any type of artificial intelligence is more like alien intelligence, and we have to be very careful. And this is my final argumentum ad verecundiam. Wittgenstein, if a lion could speak, we wouldn't understand them simply because their world and their world representation is so different from ours. Thank you very much.
Do you have any questions here? Audience, I have a lot of questions, but I want to give people some chance to ask their questions. Anyone online want to ask any questions? I'll start with my question. I think you mentioned that it's very easy for people to believe that people and language model are organizing different kinds of language word models. Hence, they will have very different kind of repetitions. Now, what if we want to really get a human type of word model? What it takes?
What would we do?
Yeah,
what we need to do? I think we're already doing some of the things that we would need to do to get, more, we've just heard a talk. The previous talk was on aligning representations of mobile robots with those of humans. That's already a step in this direction, right? Really actively making sure that representations are similar. But in general, to overcome this, you would have to have, I think, artificial agents that do the things that humans do. Navigate in the real world, that's maybe okay with robots, but most of all, I think also have dialogues, and this is points that David Schlang, the paper that I pointed to earlier, has made, kind of experience the social consequences of their linguistic behavior. So as long as a chatbot can just, hallucinate and say false things, or right, there's hardly any, corrective mechanism for that. So I think bringing in stuff like commitments and maybe social sanctioning for the kind of behavior that you show in social interaction is very important as well.
So for the second point, I think about some kind of like social learning setting where you have a model that learns with human or maybe learns with each other, but with some kind of human like kind of constraint, social constraint building.
Yes.
that makes sense to me. And I think we are
We're out of time.
time.
Yeah, thank you very much.
Yeah, thanks for the talk. So